Hi guys, today I'm going to talk to you briefly about the Epson C3 Robotic Arm, a high accuracy, high torque, 6 degree of freedom industrial robotic arm. This presentation will cover a quick introduction to the C3 Robotic Arm and RC180 controller, a breakdown of the functionalities of the RC Plus 5.0 software, a demonstration of the functionalities of the RC Plus 5.0 software, an introduction to the SPEL Plus language, a breakdown of the basic motion commands in SPEL Plus, and a solution to implementing continuous motion over TCP/IP. The Epson C3 is a compact 6 degree of freedom robotic arm designed primarily for pick-and-place use. It is driven by either an RC170 or RC180 controller, a compact controller with Ethernet and USB connectivity that runs on Epson's proprietary SPEL Plus language. The RC Plus 5.0 software is a suite that features a full simulator, including virtual TCP/IP communications in the full version of RC Plus, an SPEL Plus programming environment, also featuring command line functionality, and a robot manager and configuration interface. To start out, the user first needs to connect to a controller. This can be a real controller or a simulated controller. In this case, I'm using a simulated controller, so in order to visualize what I'm doing, I need to open the simulator window. The RC Plus simulator allows the user to place objects of many different geometries in the scene. It is also able to detect collisions between the robot and these objects. We are able to test our SPEL Plus code on the simulator by running it using the Run pop-up window. This is a simple demonstration of a pick-and-place implementation using the C3. We're able to also issue commands using the command window. The SPEL Plus language is a proprietary robot controller programming language designed by Epson. It runs natively on their range of industrial robot controllers, such as the RC170 and RC180. The language features a rich library of robot control and motion commands, serial input and output commands, multi-threading commands, and system management commands. It also features a number of mathematical functions, logical operators, and control sequences, as is expected from a programming language. As is expected from a programming language. Since the language and controller have native support for TCP/IP communications, we are able to interface with the controller from any TCP/IP enabled device. There are three basic motion commands in the SPEL Plus language: jump, go, and move. The jump command is specifically designed for pick-and-place applications, and consists of an upward movement in the Z direction, followed by a movement in the XY plane, and finally a downwards movement in the Z direction. The go command entails a point-to-point movement in the X, Y, and Z axes, neglecting the path between the 2 points. The move command is similar, but the path is linearly interpolated between the points. While the move command tends to be more predictable, there are some instances in which it will be unable to find a solution, as the linear path between the two given points is undefined for some values. In addition to choosing between go and move, the user is also able to specify a continuous or non-continuous motion profile. In non-continuous mode, the arm accelerates and decelerates at the beginning and end of each movement, respectively. This is to prevent unnecessary wear and tear as a result of abrupt stops and starts. In continuous mode, the robot moves at a constant velocity throughout the course of the movement. With continuous motion, we are able to issue sequential motion commands resulting in smooth motion along an arbitrary path. Issuing commands over TCP/IP is not too difficult a task. Since the SPEL Plus language features good support for TCP/IP communications, receiving commands is relatively simple. In addition to this, the SPEL Plus language has a dedicated function for passing delimited strings, allowing the user to send multiple values in a single transmission and interpret the transmission with relative ease. This way, we can send one pose update every transmission. The problem lies in updating the pose value without interrupting the controller's read cycle. We can do this by establishing a multi-threaded programming approach using the XQT command, with one thread dedicated to handling the TCP connection and receiving, passing, and writing numbers to a set of global variables, and another thread dedicated to executing motion commands, which take the global variables as arguments. The two threads pass a token between each other for permission to access the global variables in order to prevent simultaneous attempts at reading and writing. Setting up continuous motion on the arm is relatively simple. However, there are some limitations to the functionality. Since we can't guarantee that the pose supplied to the robotic arm will constitute a valid command, we need to ensure all commands sent to the robotic arm will work, or we risk causing an error, meaning the arm will shut down and the operation will stop. Or worse, we risk crashing the arm. Errors can be mitigated by avoiding singularities, which can be handled by monitoring joint angles during operation, and ensuring that whenever the robot nears a singularity, a subroutine takes over and forces the robot past the singularity. In the context of this project, crashing the arm is relatively easy to avoid. The only obstacles within reach of the robotic arm are a bench and a wall, both of which are planar in nature. By using the plane functionality and some simple geometry, avoiding collision with the bench and wall will be relatively easy. The controller already ensures self-collision is avoided. In addition to this, we need to make sure to handle erroneous or noisy inputs correctly, for fear of damaging the arm due to high acceleration. We can do this by setting maximum joint speeds and accelerations using the speed and accel commands. Also, we will implement a low-pass filter on the input to mitigate the effects of a noisy input. The go and move functions are able to be overridden during execution, meaning that manually interpolating towards the target pose is unnecessary.